In the last few lessons, we've talked about polynomials, what they are, how to graph them, and how to perform the usual operations on them, like addition and subtraction, and so on. With these ideas in mind, I'd like us to move to a discussion of how to solve polynomial equations. We'll spend a few lessons on these ideas, beginning with this lesson. Now, it would be nice if there was some sort of quadratic formula for all polynomials, but mathematicians have actually proved that such a formula can't exist for all polynomials, especially polynomials of really large degree. We're going to need to do something different in order to find solutions of polynomial equations where the degree of the polynomial is at least 3, for example. So in this lesson, I want us to focus on some very special polynomial equations which can still be solved by factoring. These will fall into two basic categories. Those polynomials which can be factored down pretty easily into some quadratic pieces, which can then be factored in the ways we've seen in the past, and those polynomials whose shapes or structures make them very easy to factor. These are going to include the cases that are commonly called difference of two squares and difference of two cubes. So, with this background in mind, let me begin with an example which falls into the sort of easier category. Here's the example. Solve the equation x to the fourth minus 7x cubed plus 12x squared equals 0. Now, at first glance, you might be thinking, how in the world do I even begin that kind of a problem with this quartic polynomial on the left-hand side? Well, don't worry. There's actually a nice trick, if you will, that you want to use here. In fact, in any kind of factoring problem that you encounter, you should always do the following step first. You should always look for a common factor among all of the terms in the polynomial that you're dealing with. So notice that there's actually a term of the form x squared that's common to all three terms on the left-hand side. What I mean by that is, you can factor out an x squared from every one of those three terms with no trouble. And when you do that, you can rewrite the original equation as the following. It started out as x to the fourth minus 7x cubed plus 12x squared equals 0. Factoring out that x squared gives you x squared times x squared minus 7x plus 12 equals 0. Now, if you don't believe me, you could check that by multiplying that x squared back into all those terms and then simplifying to make sure you get back to the original equation. But now we're sort of undoing that. We're sort of doing that backwards. Now I want you to notice that the polynomial inside the parentheses now is quadratic. It's a quadratic trinomial, to be exact. And since it's quadratic, you and I know many different ways to attack that part of the problem. So, let me suggest that you try this on your own. Factor x squared minus 7x plus 12. Okay, well in this case, that polynomial factors pretty nicely. And once you go back then to the original equation, you're going to have x squared times x minus 3 times x minus 4 equals 0. The x minus 3 times x minus 4, when multiplied back together, would give you the x squared minus 7x plus 12. So now you have x squared times x minus 3 times x minus 4 equals 0. What are the solutions of the equation now? Well, you want to know when x squared equals 0, or when the x minus 3 equals 0, or when the x minus 4 equals 0. You can actually split it into three little problems that way. And those translate, if you will, into x equals 0, that comes from the x squared equals 0, or x equals 3, which is the solution of x minus 3 equals 0, or x equals 4. So there are exactly three solutions to the original problem: 0, 3, and 4. And you're done. Now, if you had a graphing calculator or a computer program that could quickly plot some graphs, you could confirm what you and I just figured out by plotting the graph of the original quartic polynomial, x to the fourth minus 7x cubed plus 12x squared, and looking for the places where the graph crosses the x-axis. Those are the places where the original function x to the fourth minus 7x cubed plus 12x squared equals 0. If you just take a quick look at a sketch of that graph, you'll see that the graph does appear to touch the x-axis at 0, at 3, and at 4. And that confirms that 0, 3, and 4 are the solutions of that original equation. Now, by the way, let me share one quick note, a side note, if you will. Notice that the graph actually crosses the x-axis at x equals 3 and x equals 4 in the original function we were just talking about a moment ago. But notice that it only touches the x-axis at x equals 0. And by that I mean, instead of going right across the axis, it just sort of touches it or skims it, if you will. Why is that? Why the difference between really crossing at 3 and 4 and only just sitting at x equals 0, if you will? Well, if you go back to the factored form of the equation, we had x squared times x minus 3 times x minus 4 equals 0. Notice that the x minus 3 and the x minus 4 factors are basically raised to the first power. It's like an x minus 3 to the 1 and an x minus 4 to the 1. And 1 is odd. But also notice that the x that's in the front is squared. There's an x squared term there, which is sort of like an x minus 0 squared. And of course, the power of 2 is even. That even power on the x means that when the x values are close to 0, the graph has to stay above the x-axis. There can't be any negative y values there. And this idea is going to come into later examples and even later conversations that we'll discuss. So sometimes you're going to cross, and that happened here with an x minus 3 times an x minus 4, both of which were raised to an odd power. And sometimes you're just going to touch the axis, maybe from above, maybe from below, and that's going to occur when that factor has an even power. And we'll talk about that some more in future conversation. Now, I'd like to look at another example of this idea of factoring out a common term. As I said earlier, it's the first thing you should always do when you're doing these kinds of problems. So let's start with this. Solve 2x cubed minus 10x squared equals 12x squared minus 56x. Okay, the first thing you should do here is subtract all the terms from one side over to the other side. I'm going to suggest we subtract the terms that are on the right-hand side over to the left-hand side so that we get all the terms equal to 0. So let's do that first. We started with 2x cubed minus 10x squared equals 12x squared minus 56x. And now when we do that subtraction, we're going to have 2x cubed minus 10x squared minus 12x squared plus 56x equals 0. Combining the like terms gives me 2x cubed minus 22x squared plus 56x equals 0. Now, this polynomial on the left-hand side is cubic, and I really don't know what to do with a cubic. I don't have something like the quadratic formula for cubics. There actually is a cubic formula, but it's a very big thing. It's kind of unwieldy. So I'd like to try to attack this problem by whittling it down away from a cubic down to something I know, like a quadratic. Well, what do I do first now that I've got this equation into the form all the terms equal to 0? I try to factor out a common term before I do anything else. Now, is there a common term? Yeah. In fact, we can factor out an x, because there's an x in every one of those terms. And actually, all of their coefficients are even, which is a hint that you can factor out a 2. So we can actually factor out 2x. And when I do that, the equation is going to become 2x on the outside times x squared minus 11x plus 28 equals 0. And now if you see, this is like the earlier example. The part of the equation in the parentheses is now quadratic. Its degree has been reduced down to 2. And I know how to attack those kinds of guys. We've handled those with several lessons in the past. So let's see if we can factor that quadratic polynomial and then take the problem from there? Well, we can. That piece inside parentheses is actually equal to x minus 4 times x minus 7. And so my original equation now has been rewritten. It's the same equation, except that it's in a totally different form. It now looks like 2x times x minus 4 times x minus 7 equals 0. So, what are the solutions? If I find the solutions of this equation, I have found the solutions of the original equation. And the solutions here are x equals 0, that comes from the 2x in the front, x equals 4, and x equals 7. Now notice that each of the terms in the polynomial equation is raised to the first power. 2x to the 1, x minus 4 to the 1, x minus 7 to the 1. All of those are odd powers. And that means when I graph this polynomial and I look for those x-intercepts, I'll actually have 3 of them, at 0, at 4, and at 7, and they will all actually cross through. They'll cut through the x-axis at every one of those 3 points, not just touch the x-axis at any of those spots. And if you look at this graph, you'll see that's exactly what happens in this case. Now, you might be thinking, I see a pattern here. When I perform this idea of factoring out a common term, I'm always going to get a quadratic inside the parentheses, and then we'll factor. Well, that would be guessing a little too much of a pattern, I'm afraid. It's not always going to be the case that you'll get that. So let me show you one more example of this kind of work, just so you can see some of the variety that can actually occur. In fact, let me suggest you try this one yourself. Solve the polynomial equation 4x cubed plus 6x squared equals 0. Okay, so what did you find? Well, I'm going to start, I hope you started, by factoring out the common term. And in this case, you can actually factor an x squared out of both terms, and you can factor a 2 as well from the 4 and the 6. And when you factor out the 2x squared, you're left with 2x plus 3. So the original equation becomes 2x squared times 2x plus 3 equals 0. And now the polynomial that's left inside the parentheses is not quadratic, it's just linear. It's just raised to the first power. So there's actually no more factoring that has to be done. Your solutions are pretty quick, pretty easy to find. They are x equals 0, which is coming from the x squared term, and x equals negative 3 halves. Now, where did that x equals negative 3 halves come from? Let's just check quickly. When you look at the 2x plus 3 equal to 0 and subtract the 3, it's the same as 2x equals negative 3, and then dividing by the 2 will give you x equals negative 3 halves. So those are my two solutions, x equals 0 and x equals negative 3 halves. And just to keep with this idea of looking at the graph one more time, the graph is going to just touch the x-axis at x equals 0 because the x is raised to the second power and that's even. But the graph is going to completely cross the x-axis at x equals negative 3 halves because the 2x plus 3 is just raised to the first power and that's odd. If you look at the graph of the original polynomial that we started with, you'll actually see this in that graph. So we've seen that one way to solve polynomial equations where the degree of the polynomial is larger than 2 is to just start by factoring out a common term, which is often some sort of monomial, some sort of one-term piece that you can pull out. But there are lots of other tricks we can use to factor and solve polynomials that have relatively large degree. One of them is to look for very specially shaped polynomials, if you will, that have a certain structure to them, which are known as a difference of two squares. In one of our previous lessons, I spoke about polynomials which demonstrate a difference of two squares, and the name tells us exactly what we mean. For example, take the quadratic polynomial x squared minus 25. That is a difference of two squares. Why? Well, x squared, of course, is a square because it's x times x. And 25 is a square because it's 5 times 5. And we're taking its difference, x squared minus 25. So when I say that I'm looking at a difference of two squares, I literally am looking at a square minus another square. And then in that lesson, we learned that when you have a difference of two squares, it's easy to factor. In the case of x squared minus 25, it's the same as x minus 5 times x plus 5. And the x, of course, is acting like the square root of x squared, if you will, and the 5 is the square root of 25. So that's where the pieces of that factorization come from. But how might we use this to solve polynomial equations of higher degree? Well, let's think about the following example. I want us to solve x to the fourth minus 81 equals 0. Now, your first thought might be, wait a minute, x to the fourth isn't a square, it's a fourth power, it's x raised to the 4. But that's just one way to look at it. I can also think of x raised to the fourth power as x squared squared. So x to the fourth really is a square, it's just x squared squared. And of course, 81 is 9 times 9, so it's also a square. And that means that the original equation we started with really is a difference of two squares. It's just kind of hiding a bit as a difference of two squares. So the original equation, x to the fourth minus 81 equals 0, can be rewritten as x squared squared minus 9 squared equals 0. And now using this idea of difference of two squares factoring, I have x squared minus 9 times x squared plus 9 equals 0. If you don't believe it, FOIL that left-hand side and make sure it comes back to x to the fourth minus 81. But guess what? After doing this factoring and getting x squared minus 9 times x squared plus 9 on the left-hand side, we're not done, because the x squared minus 9 can still be factored. It's also a difference of two squares. So I can actually do one more level or layer of factorization. And instead of stopping at x squared minus 9 times x squared plus 9 equals 0, I can actually write x minus 3 times x plus 3 times the x squared plus 9 equals 0. Now, that left-hand side of that equation will no longer factor. At least it won't factor using real numbers, okay? So that is as far as we want to go with that factorization. And it means that I now know my real number solutions. They're going to be the x equals 3, which comes from the x minus 3, and x equals negative 3, which comes from the x plus 3 factor. And these are the only two real number solutions that I'm going to see in this equation. Now, what does that mean as a graph? It means that if I go back to the graph of x to the fourth minus 81, that was the original left-hand side of the equation, that graph will only cross the x-axis in two places, x equals 3 and x equals negative 3, and it really will cross through or cut through the x-axis at those 2 points. And remember, degree 4 polynomial is what we started with, but I'm saying here it only has 2 x-intercepts. Remember, that's okay. Even though we started with something of degree 4, we are allowed to have fewer than 4 x-intercepts if needed. Now, I'd like to look at one more example of a difference of two squares, and then we'll move forward from there. Let's solve the equation 2x to the fourth minus 32x squared equals 0. Now, I can hear some of you saying, wait a minute, you just said you wanted to do difference of two squares, but 32 isn't a perfect square, and neither is 2. What in the world are you doing? Well, you've got to remember our first rule of thumb. Always factor out any common factors before going further. So let me suggest you now do that step yourself before we get back together. Solve this equation 2x to the fourth minus 32x squared equals 0, remembering to first factor out the greatest common factor. Okay, now what is that greatest common factor? Well, in this case, you can factor out an x squared and you can factor out a 2. So if you start with the original equation and you factor out a 2x squared, you're going to have 2x squared times x squared minus 16 equals 0. And now you say, I see the difference of two squares. The x squared minus 16. X squared, of course, is a square. It's x times x. And the 16 is 4 times 4, and they're being subtracted from one another. So that factor, x squared minus 16, is a difference of two squares, and it will factor And that means that the original equation can be rewritten as 2x squared out in front times x minus 4 times x plus 4 equals 0. And now you've factored this completely, and you can read off the solutions very quickly. There are 3 of them: x equals 0, x equals 4, and x equals negative 4. Now, I'd like to transition into one of the other special types of polynomials that I mentioned earlier. Difference of 2 squares is one of those special types, but there's another one. It's actually 2 of them, but they kind of land in the same category, and they're known as difference of 2 cubes and sum of 2 cubes. Now, rather than getting all long-winded about them, let me just show you their formulas first. If you start with a cubed minus b cubed, that's going to be a difference of 2 cubes because you're subtracting. It turns out that a cubed minus b cubed always factors. And it factors as a minus b times a squared plus ab plus b squared. That's the difference of 2 cubes. And now there's a sum of 2 cubes formula as well. A cubed plus b cubed equals a plus b times a squared minus ab plus b squared. Now, before we look at some specific examples, let me say this. If you don't believe that these formulas are really correct, all you have to do is remultiply out the right-hand sides of the equations I just showed you and combine the like terms. And you'll see after you do that, that the left-hand side, whether it's a cubed minus b cubed or a cubed plus b cubed, is just going to pop out. It'll really work. So these factorizations work very nicely. One of the warnings I'll give you is that sometimes it's hard to remember them correctly. Is there a minus here? Is there a plus there? What's happening there? So if you're going to use difference of 2 cubes and sum of 2 cubes, you have to be very careful to memorize them correctly and then to practice them quite often to make sure you use them right. Now, let me show you how these might come in handy. Here's an example of an equation that I think is most easily solved using difference of 2 cubes. Find all the real number solutions of x cubed minus 27 equals 0. Now, this is a difference of 2 cubes. I've got x cubed, that's obviously a cube, and 27 is 3 raised to the 3rd power. It's 3 cubed, so that's a cube, and I'm taking the difference because I'm subtracting, so I can just use the formula. And it tells me then that the original equation, which was x cubed minus 3 cubed, is the same as x minus 3 times x squared plus 3x plus 9. By the way, I went back to those formulas that I showed you earlier, and I let a equal x and b equal 3 in order to get what I just had. So I now have x minus 3 times x squared plus 3x plus 9 equals 0. Now, one of the solutions of that equation is just when x minus 3 equals 0, and that, of course, is the same as when x equals 3. So that's easy. So there's definitely one solution, x equals 3. Now, what about the x squared plus 3x plus 9 equal 0 part of this problem? What happens when you try to, say, apply the quadratic formula and get some solutions? Well, in the case of studying x squared plus 3x plus 9 equals 0 using quadratic formula, you're going to have the following solutions. You're going to have x equals negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 9, all divided by 2 times 1. And that's the same as x equals negative 3 plus or minus square root of 9 minus 36, all divided by 2, which is the same as x equals negative 3 plus or minus square root of negative 27, all divided by 2. Notice that the quantity under the square root, which you'll recall we called the discriminant a few lessons ago, that discriminant is negative. It's negative 27. And it means that we're going to need the value I to come into play if we're going to find these solutions, and that means that these will not be real roots or real solutions. They're going to have to be complex, again, because that discriminant is negative. And therefore, it means that we really only have one real root, and it was at x equals 3. We found it a moment ago. And what does that mean about the graph of the original cubic polynomial I started with? Well, if you draw the graph of x cubed minus 27, it means that you'll only have one place where you have an x-intercept, and it's going to be at x equals 3. And a quick sketch of that graph shows you that pretty quickly. Now, let's look at one more problem of this type. Again, for the practice, I think it's very important that we do this sort of thing, because identifying these problems is just as important as being able to actually go through them. By the time this course is over, you're going to have a very large toolbox, so to speak, of tools to do these problems. And you have to know which tool to grab from the box in order to apply it to the problem before you can ever solve the problem. So let's look at another example. Find all the real number solutions for the equation 40x cubed plus 5 equals 0. Now, you're staring at this problem and you're thinking, look, 40 isn't a square and it's not a cube. I have no clue what Sellers is doing. Does he even know what he's doing? Well, don't forget, first rule of thumb when you're doing these problems of solving these equations, factor out the common term, and then maybe something will become more obvious. In the case of 40x cubed plus 5, the common term is 5, because 5 will divide 40, and of course 5 will divide 5. Factoring out a 5 will give me a new way to write the equation as 5 times 8x cubed plus 1 equals 0. Okay, that 5's not going to provide me with any solutions for x. It doesn't have any x's in it, so I can just divide it out if you want to think of it that way. And now I just really want to focus my attention on 8x cubed plus 1 equals 0. Okay, now I see an x cubed. That's nice. It's got an 8 in front of it, though. And then there's this plus 1. So we're not looking at a difference of anything because we're actually adding. We must be doing a sum to have that plus between the 8x cubed and the 1. But is that really a sum of two cubes? That would be a nice tool if we could use it here. Well, 1 is the same as 1 cubed. It's also 1 squared and 1 to the 4th and a lot of other things. But for us right now, we want it to look like 1 cubed. Now, what about the 8x cubed? Can you write that as a cube? Well, think of it this way. Think of it as 2x times 2x times 2x. And if you think of that, that really is 8x cubed. And that means 8x cubed is the same as 2x cubed. Therefore, my equation really is the sum of two cubes. It's 2x cubed plus 1 cubed. And if I just let a equal 2x and let b equal 1, then I really have a sum of two cubes, and I can use the formula that I showed you a few minutes ago. So 8x cubed plus 1 can be rewritten as 2x plus 1, that's the a plus b, times the quantity 2x squared minus 2x plus 1. And of course, that's all equal to 0 once I start writing my equation. And simplifying that just a bit, it's the same as 2x plus 1 times 4x squared minus 2x plus 1 equals 0. And now I've got two problems. I want to know when 2x plus 1 equals 0, and I want to know when 4x squared minus 2x plus 1 equals 0. Well, the first term, 2x plus 1 equaling 0, is going to give me the solution x equals negative 1/2. Again, write down 2x plus 1 equals 0, subtract the 1 over to the right-hand side, divide both sides by 2, and you'll get x equals negative 1/2. So that's a real solution. What about the quadratic part, the 4x squared minus 2x plus 1 equals 0? Well, you can again apply the quadratic formula just like I did in the previous example, and you're going to find that the solutions you'll need will be complex. Again, that's going to be because the discriminant is going to be negative. The part under the square root symbol in the quadratic formula will be negative. And therefore, that will not provide you with any real number solutions. And that means there's only one real number solution, x equals negative 1/2. And that came from the 2x plus 1 term that we had out in front. Now, I'd like to close with one more example of how to see these polynomial equations, just to make sure that we've got the right idea in order to do these. So here's the example. Find all the real number solutions of x to the 4th minus x squared minus 30 equals 0. Now notice something, there's no common term to factor out. So that whole thing I've been telling you about factor out common term, well, there isn't one. So I'm going to skip that. And I see that this isn't a difference of two squares. It's not a difference of two cubes. And it's not a sum of two cubes. So maybe I just have no clue how to do this. Well, I actually do. I want you to see how to look at this polynomial a little bit differently. Think of the x to the fourth as x squared squared. And of course, think of the x squared as just x squared to the first. Then what you really have is x squared squared minus x squared to the 1 minus 30 equals 0. What if you changed all of the x squareds to t? Just let them be called t. Then what you would really have is just t squared minus t minus 30 equals 0. Do you know how to do that? Sure, you just factor. And when you factor t squared minus t minus 30 equal to 0, it's the same as t minus 6 times t plus 5 equals 0. So t is 6 and t equals negative 5 are the two solutions. But we should write these back in terms of x because we started the problem with x's. So if t equals 6, it's the same as x squared equaling 6 because t was equal to x squared. And if t is negative 5, then x squared is negative 5. Now what are the solutions? Well, when x squared is 6, the solutions for that will be square root of 6 and the negative square root of 6. And both of those are real solutions. So I have two real solutions, square root of 6 and negative square root of 6. What about the other one? X squared equals negative 5? No real solutions there. Never can there be a real number, x, so that when you square it, you get negative 5. And therefore, there really are only two real number solutions. And they're going to be x equals the square root of 6 and x equals the negative square root of 6. Now, with that said, I'd like to close out today's lesson and look ahead to the next lesson. We're going to continue talking about this idea of recognizing what a polynomial looks like, and we're going to continue talking about these ideas of solving polynomial equations. I'll see you then.